Hi, my name is Alexander Jarrett. My partner is Theo Harris Puga. We are ME54, and our project is to build a controller for a 1.5 kilowatt BLDC motor. This project is sponsored by Triumph Group and is joined with ECE 2229. Its group members are Bolivar Baez, Jacob Parent, James Hipsky, Jan Fayen. Our faculty advisor is Dr. Cheng Yu Kao, and for the electrical team is Dr. Sung-Yul Park. Our sponsors are Dwayne James, Joe Borelli, Lou Panulo, Justin Huddy, and Michael Danner. A few words about our sponsor. Triumph is a leading company in aerospace and aviation structure components. Triumph is currently expanding their market in BLDC motors, and the goal for this project is to build and manufacture a controller that will drive a 1.5 kilowatt motor and can operate between negative 40 degrees to 85 degrees Celsius. The motor will not be inside the controller and should be air-cooled with no use of fans. Our team approached this project in three parts. The first part is the PCBs and the enclosure. The second part is thermal management, and the third part is analysis of the motor.
So for the first part, the mechanical design, we worked with the team to develop the layouts and decided to have two different boards. An IMS board made of aluminum, which is the lower board that will contain most of the electrical parts, and the FR4 board, the upper board, that will host the processor board and fewer circuits. Our team handled the board layout such as the exact location of connectors and mounting parts to support the PCBs inside the enclosure. Next, based on the dimensions of the PCB, we designed a box made of aluminum with 16 mounting holes for military spec 632 screws and 3/16 inches wall thickness for support. The enclosures designed was made such that there was approximately half an inch space between the boards and the housing, so that allows us to place the PCBs inside the housing. Notice that the box doesn't have a tap, and this was a decision made to keep the temperature down by convection. Following this, our team decided to manufacture a heatsink on the bottom of the housing instead of purchasing one. Here, we calculated that for a base thickness of 0.6 inches, fin thickness of 0.185 inches, and 20 fins, if we had 50 watts of heat dissipation from the PCB for an airflow of 0.1 meters per second, which is room conditions, the housing would reach 50 Celsius of maximum temperature, which wouldn't exceed the temperature requirement. For the second part of the project, we ran thermal analysis on the controller. We assumed convection outside of the inside and inside of the box's surfaces. According to heat dissipation of 50 watts and 10 watts on each board, that was calculated from big electrical components, we applied power heat generation, and the ANSYS showed that the controller would not have a max temperature of 39 Celsius on the processor and a low temperature of 34 Celsius around the IMS. Moreover, the team was concerned on the IMS board since 6 MOSFETs that it contains would generate 3.2 watts each, as shown on the left picture. The lower board would effectively generate the heat so that the temperature would not pass 35 Celsius, also taking into account that the MOSFET's max temperature cannot exceed 150 Celsius. As a result, no necessary heat sinks were added on the boards. Based on the video, this was a successful heatsink design. The temp of the box does not pass 35 Celsius, and it generates the heat of the MOSFETs very well. Plus, it's in the sponsor's temperature requirement of the enclosure.
For the third part of our project, our team had to test a motor that will be driven from the controller. As shown on the left picture, the team's plan was to mount a motor with a dyno and get important information from the controller and provide it to the electrical team, such as load, torque, efficiency, and RPMs. But because of a laboratory accident in March, the dyno got burnt. We found a new dyno, but it wouldn't match the motor. We designed and manufactured a new structure, as shown on the right, that will match the height of the motor and the new dyno. We will have the new structure and test the motor by the second week of April. For our last part, our accomplishments. We designed the layout of the IMS and FR4 board, designed and built housing to mount PCBs, the thermal management of the controller to match our temperature goals. We built the structure to connect the dyno and the motor for testing purposes. And lastly, our recommendations for the sponsor. For the design, to have a closed top on the housing so there's no accidents. For the thermal, to incorporate a fan so that everything can be cooled down. And then for the heat sinks, to have thermal pads in the hot parts of MOSFETs and regulators to keep the temperatures less than 35 degrees Celsius. Thank you for listening.